As far as audio effects go, Echo is not the only game in town. There's so much cool stuff that you can do with audio. Back in the day, when I was a student, I and my trusty amp would roam the countryside making amazing music. And of all the dials on that amplifier, well, of course, my favorite is the master volume, but then after that comes the guy at the end, the reverb dial, which gives you this really cool effect of being in this gigantic concert hall. Reverb. Now, if you're not familiar with reverb, you've got to spend a little bit of time listening to it, thinking about the audio characteristics of this. It might be worthwhile to think about what happens when you have just a pulse as an input, like this. And then looking at what happens when you feed that into a reverb. Okay, all set. Now, as a digital effect, reverb, just like echo, converts a signal, U, to an output, X. And it does so by an affine relationship. We can write this as a kth order recurrence relation, where k is the size of our window, our sliding window that we're using to inspect and then modify the signal. Here's the recurrence relation. xn plus 1 equals alpha xn plus alpha squared xn minus 1 plus, and I keep going until at the end I've got alpha to the k, xn minus k plus 1. That's the linear part. Then I add in the user input u sub n. Now again, just as with the echo, this alpha is a gain. This is going to be some constant that is positive, but that guy needs to be much less than 1. Don't put that guy anywhere near 1 or what a mess. Now, of course, what we're going to do is we're going to take this recurrence relation and vectorize it and pull out the matrix, the k by k matrix for this system. The system converts to EX equals some matrix A times X plus our user input signal that has UN in the first slot and zeros below. That matrix has a really nice block structure where what you have is an identity matrix in the k-1 by k-1 block in the lower left-hand corner that shifts the signal ahead one time step. You have zeros in that last column. And then all along the top, you have these coefficients. Alpha, alpha squared, alpha cubed, all the way up through alpha k. And now you look at that matrix and you say, aha. Because, of course, when you pull this matrix out, you look at it and you say, oh, I've seen this before. This is just like the age cohort model for population, where we have those reproduction rates along the first row. But what's a little bit different here is that when we were looking at age cohort models with reproduction rates, let's say you have a lot of different age cohorts, then typically those reproduction rates are going to follow some sort of unimodal distribution. They start off really, really small, maybe 0, and then they climb up, and then towards the end, they taper back off again. Now, this is much different with reverb. If you look at that first row, then what do we have? We have increasing powers of alpha, but because alpha is less than 1, a fair bit less than 1, then these reproduction rates are falling off exponentially. And that's really related to this fluttering sound effect that you get in a good reverb. It is all due to the eigenvalues of this matrix, and that's what we want to turn to. Because unlike the case of the echo, this system has a dominant eigenvalue. When alpha is positive, this dominant eigenvalue, lambda star, is also going to be positive, and the eigenvector associated to it can be chosen to have first component 1, and then all of the remaining components inverse powers of this lambda star. So lambda star to the -1, to the -2, all the way up through 1 minus k. Now notice that because alpha is less than 1, this dominant eigenvalue, lambda star, is also going to be less than 1. So what does that mean about this dominant eigenvector. The other thing to keep in mind is that unlike in the straight-up linear population model, this is affine. What we're looking at here with the dominant eigenvalue, the dominant eigenvector, that's just for the linear part. That input signal is what's really driving the sound, and that makes a big difference also.